Next topic for us are the states and properties of matter. So for this class, we are going to discuss, basically have our physical states. I also call these phases. There are 3 of them. We have solid, which we give the symbol of a lowercase s in parentheses. We have a liquid, which we have a lowercase l in parentheses. I like to put my lowercase l's as a cursive L so I can distinguish it from my ones. And our third is a gas, which has a lowercase g. So there's a table in your book that kind of goes through the characteristics of solids, liquids, and gases. You'll want to consult that. I'm just kind of going to pull out 1 or 2 properties for each of these different phases, but you'll definitely want to look at the other ones. The solid, okay, whenever we're looking at something that's solid, one of the things that defines it is that it is something that's going to have a definite shape and have a definite volume. If we think about this more on a atomic level, so kind of zooming in really close on our molecules here, in a solid, basically the atoms or the molecules, depending on what we're looking at, they're going to be very, very close. Okay, they're basically touching, oops. And in most solids, they are so close, in fact, that they basically cannot move. They are as close as they can get to each other. Okay. Now, in chemistry, when we have atoms or molecules that are very close, what this means is that they're going to have very strong attractive forces between the molecules. Our liquid has some similar properties to a solid. One of the things where it differs is it's not going to have a definite shape. So no definite shape, but it will have a definite volume. Like a solid, the atoms or molecules are close to each other, but they're starting to separate a little bit. Okay, so in the solid, they're touching, they're very close, they basically can't move in their position. In a liquid, they're starting to separate, they're still touching, but they can kind of slide past each other. So our atoms and molecules are close, but can slide past each other. So when we kind of have this movement, this sliding past each other, we kind of call that sufficient attractive forces. So the molecules are still attracted to each other, but they're starting to kind of try and want to find their own way. Gases are completely different. They basically have no definite shape and no definite volume. And in a gas, basically our atoms or molecules are as far apart as possible. So they do not want to touch each other whatsoever. And they are free to move around as much as they'd like. So when we talk about gases, there's essentially no attraction there. Those molecules are completely satisfied with being by themselves. All right, so these are our physical states. We can convert or change a compound to go in between these states, and we call those our changes of states. Okay, so we have a number of different changes that we can do. So again, we use the word state or phase interchangeably. So we can look at basically the changes that occurs between a solid, a liquid, and a gas. So if we go from a solid to a liquid, that is called melting. And most of the time when I'm thinking about these solid liquids and gases in my phase changes, I'm usually thinking of water. You probably experienced it in all three phases very commonly. So this is basically your ice, this is liquid water, and water vapor. So if we take ice and we want to turn it into liquid, we melt it. The technical term of this is called fusion. If we keep adding energy, we add heat. We want to take our liquid into our gas. So we want to go from liquid water to water vapor. This is called vaporization. Or you might want to call this boiling. If we go in the opposite direction, if we go from a gas to a liquid, we call this condensation. Usually what happens to your windshield overnight, most of the time in the Pacific Northwest. And since it's winter, if it gets cold enough, we can take that liquid water and we can freeze it into a solid. Okay, so this freezing. We have two more changes of states that aren't very common, but they do happen. Okay, and the first one is going from a solid directly to a gas without ever existing as a liquid in between. Okay, this is called sublimation. And dry ice does this at room temperature. If you've ever dealt with dry ice, it's a solid and it goes directly into a gas vapor. If we go the opposite direction, if we go from a gas down to a solid, okay, this is called deposition. And those are our different conversions between our changes of state. Now, since this is a chapter about energy, okay, we do have our changes of state, we can associate a certain amount of energy it's going to require to complete these different changes of states. And these are called your heats of fusion, okay, going between a solid and a liquid, or your heat of vaporization between a liquid and a gas. So let's first off talk about heat of fusion. The symbol that we give this is a capital H, and then as a subscript we have FUS for fusion. Your book refers to this as heat of fusion, and it just does it very, very briefly. It doesn't discuss it very in depth, so we're going to spend time here discussing it. Your book calls it just a heat of fusion, okay? But the rest of the world calls this enthalpy of fusion. And that's because this capital H here actually does not stand for heat, it stands for enthalpy. It's one of our physical properties, which we'll talk about those more momentarily. Okay. Basically, what our heat of fusion or our enthalpy of fusion is it's the amount of energy needed to separate the particles of a solid. So remember, one of the definitions of our solid versus a liquid is our solid, our molecules are very, very close together, okay, whereas our liquid they're starting to separate. So how much energy goes into separating those molecules, going from a solid to a liquid? That's the heat of fusion. So when we talk about heat of fusion, this is going to involve going from a solid to a liquid. Okay, and when we do that, basically we have to add heat. And we use the word heat and energy interchangeably. So if we go from a solid to a liquid, we have to add heat. If we go the opposite direction, if we go from the liquid to the solid, okay, basically we're going to have a loss of heat. So heat's going to come off of that. Each substance has its own H of fusion. And we can look those up into tables. For homework and exams like that, values would be given to you. But basically each substance has its own H of fusion. So for example, water, so H2O, has an H of fusion of 334 joules per gram. Oh, that's one thing that we can add over here. Usually the units are going to be joules per gram. Remember, joules is a unit of energy, and it's always a capital J, no lower cases. Or on occasion, you can see it in calories per gram. So let's work through an example of using this. Okay. Remember, whenever we see these two units, something per something, we can use it as a conversion factor, right? So if we have an example here, we want to know how many how much energy, so how many joules, is needed to melt 20 grams of ice. We have our heat of fusion here, and that's going to allow us to basically convert between grams and joules. So if we start out with our 20 grams of ice, multiply that by our heat of fusion, 334 joules per gram. Our grams cancel. We have 20 times 334, which is 6,680 joules. So that's how much energy it's going to take to melt 20 grams of ice. Now, for those of you who like equations rather than looking at units, basically we can derive one from this. If you take your mass times your heat of fusion, this will get you your energy or your heat. Same thing. So that's your equation that you can work with. All right. Heat of fusion will also work. Okay, if we wanted to then take this now liquid water and freeze it again, okay, the value, the numerical value of that energy stays the same. It's just whether or not you are putting heat in or you're taking heat out. Okay, so it's going to take 6,680 joules to melt 20 grams of ice. Okay, we have to put in that amount of energy. If we were to freeze 20 grams of water, it would give off 6,680 joules of energy. Okay, so heat of fusion works both for melting or your fusion as well as your freezing. All right, let's talk about our other transition between liquids and gases. So we're talking about our vaporization. So we have heat of vaporization next. So we have capital H, and we put VAP as our subscript. Okay? And again, this H doesn't stand for heat. It's called enthalpy. So kind of the rest of the world calls this enthalpy of vaporization. And it's basically the same concept as our heat of fusion. It's just going from a liquid to a gas. So the energy, this heat, it's the amount of energy required to vaporize something from a liquid to a gas. So now we're involving going from a liquid to a gas. In order to make that transition, we're going to have to add heat or add energy. If we go in the opposite, remember the numerical value is the same. So the amount of heat involved is the same. It's just when we go from a gas to a liquid, this is going to be a loss of heat. So this is how much heat is being given off. Same concept as our heat of fusion is that each substance is going to have its own H of vaporization. So if we say we're still working with water, we like working with water, it's very common. Basically the H vap of water would be, let's work in calories just because we can. get some practice with those units. We'd have 540 calories per gram. So let's do an example. So calculate the amount of heat released when 25 grams of steam at 100 degrees Celsius condenses. So again, we know that our heat of vaporization, our enthalpy of vaporization, is 540 calories per gram. And we know that our mass of our steam is 25 grams. This 100 degrees Celsius, all that tells us is that we're at the boiling point of water. So we know that there's no other energy things going on. We'll talk about that more in section 2.5, and then we're going to combine 2.4 and 2.5. So stay tuned for more on that. But for this problem here, what we want to do is we're going to follow kind of the same calculation that we did above here for our heat of fusion. We're going to take our mass. We have our 25 grams of water. Multiply it by our heat of vaporization. So we have 540 calories per gram. That one I'm not good enough to do in my head. So let's grab our calculator here. We have 25 times 540. So I get 13,500 calories. And my grams cancel, so all I'm left there with is my calories. So if you, again, like your equations, basically what we're looking at is we took our mass times our heat of vaporization, and that is equal to our energy, okay, or heat. So that's kind of, this would be a good time to write kind of a summary of our kind of equations here. So our summary for our equation, basically what we're looking at is our energy is going to be equal to, that's our enthalpy, our capital H, times our mass. Okay. Now, if we're involving a solid to liquid transition, so solid to liquid, liquid to solid, you're going to use your heat of fusion. And if you're going between the liquid and gas, you're going to choose your heat of vaporization. All right. Before we wrap up this conversation about our changes of state and our basically our physical and chemical properties, we want to actually discuss our physical and chemical properties. And why are they different? What makes them different? So we'll do physical versus chemical. So we'll first start with our physical properties. For our physical properties, these are basically things that you are observing or you're measuring, but you're doing it without changing the substance. So you're just you're looking, you're just looking at them. Okay. Yes, you can touch them, but we don't want to do any, say, reactions with them yet. So these are basically your descriptors. Okay, so you can describe the shape of something, the color, maybe the odor, the smell of it. Um, some physical properties that we've talked about already would be density. Okay, density we can measure without changing the subject or the substance, or what we've already talked about, like say the H of fusion, the enthalpy of fusion. Now we can also make observations or look at physical changes. These are changes that are going to occur that maybe change the appearance of what we're looking at, but it's not going to change it chemically, so it's not rearranging the composition. Okay, so basically what we're looking at for our physical changes, these are the changes in state. So your solid to a liquid to a gas. Okay, those are all physical changes. Okay, what's important for these is the composition of whatever we're looking at remains the same. So if we have water, okay, water is H2O. Okay, we have two hydrogens per one oxygen. Okay, if we have a solid ice cube, that's the molecules in there are going to have two hydrogens per one oxygen. If we melt that ice cube, we're still going to have two hydrogens per every one oxygen. We just are going to take the H2O as a solid and change its physical appearance into a liquid. Okay, but we still have the same chemical. All right, so let's talk about our chemical changes. Oh, chemical properties first. Well, for our chemical properties and our chemical changes, they're kind of silly to think separately, but we'll define them separately. Basically, our chemical properties is the ability of a substance to change into a new substance. So now we're talking about actually rearranging atoms, changing the ratios of them. So an example of a chemical property is that iron has the chemical property that it can rust. Okay. Basically, iron is Fe. Rust is what we call an iron oxide. So it's FeX. OY, and those X's and Y's can change depending on what the environment is. So we can take iron just by itself. It has the chemical property of being able to rust, okay, to change into a new substance. Now that the chemical change that occurs, if that were to happen, that's what we call the chemical change. And so that's where it actually changes into a new substance. So our chemical change then would be, say, a nail, which is usually made of iron, okay, actually rusting. And once it goes through that change, it's done a chemical change. So that wraps up section 2.4 in your book. There was a lot that we covered in this one, so you're going to definitely want to go through your questions and problems in your book. You'll also want to definitely do the sapling online learning, because that will go through working with these types of calculations. These aren't in your book, so you'll want to take these notes and work with the sapling learning online to practice doing these types of calculations.